difference between resistance and resistivity?
Resistance, resistivity, resistors. All different, and we explain in time. Okay, don't worry. Start. Yeah. So, current, we said last time, is the change in charge per time. So you might remember that we said last time Q equals I times T. That means that I, you can say, is Q over T. Or in other words, as I said, it's coulomb per second or charge per time. So another way to define current is the rate of change of charge per unit time. But you could kind of see that last time too. Okay, continue. Yeah. Continue. Yeah. Now, next, and that's it as a formula, which we just said. Next, we have something called voltage. Now, we didn't talk about voltage last time. Voltage is actually kind of like a potential energy per charge, and it's measured in joules per coulomb. So if I could try and draw that, so let's imagine we have 1 coulomb here, 1 coulomb here, 1 coulomb here, and they all move to the right, and this is A and this is B, and let's say it takes 3 seconds to do this. Then we can say the current is 3 coulombs per second. Or, as we learned yesterday, that's called 3 amps. That's okay, right? Now, it's possible that each of these guys can actually do some work, that they have energy inside of them. A bit like how when the mass is here, it has a potential energy. These all could have energy inside of them, and we call this the voltage. And it's the energy per charge, and it's measured in joules per second. So for example, if each of these could do 3 joules, or we'll say 4 joules of work, then we say the voltage is 4 joules per coulomb. So voltage is just joules per coulomb. It's how much energy each charge could do. But we don't usually use joules per coulomb. We use a different unit, and we call it the volt. But 1 volt is simply just 1 joule per 1 coulomb. That's all it is.
Is it possible that each column have different energy, different volts, 4 joule or 3 joule?
Yeah, it's possible, I suppose. But in that case, we only care about the average. So, if there's 10 coulombs and maybe it's like, he could do, or it could do 1 joule, 2 joules, 1 joule, 2 joules, then we just take the average. Right. Yeah. In fact, in real life, that probably is the case, that each one has a different one, yeah. But we don't care, we just care about an average or a total. Okay, do you have this written down? Yeah. Okay. So next, the third thing is called resistance of a conductor. So the resistance of a conductor, it measures how difficult it is for the current to move through it, and the unit is called the ohm. So what do we mean when we say 1 ohm? So when we say 1 ohm, we mean 1 volt was converted into another form, like sound, light, and heat, when a current of 1 amp passes through it. So you can write this down in a second. Let me just try and draw that. So let's imagine here we have 1 coulomb, 1 coulomb, 1 coulomb, and they'll all move through some conductor. So they're all moving in the conductor, and out they come. And if it takes 1 coulomb 1 second to move through the conductor, then what do we say the current is? We say it's 1 amp, or 1 coulomb per second. Okay? Now let's also imagine that each one of these could do 1 joule of work. So he could do a joule, and he could do a joule, and she could do a joule. So they could each do a joule of work. But after they move through the conductor, they lose this joule of work they could do. So they can no longer do a joule of work. Now we know that energy cannot be destroyed. So what happened here? It's gone. It changed. Now, it could have changed into anything. Maybe this conductor was a light bulb, and so it came out as light. Or maybe it came out as heat. But anyways, it came out and it was lost. So because it lost 1 joule, so because it lost 1 volt per 1 amp, we say then that the resistance is 1 ohm. So this drop in its ability to hold to carry potential energy, we call that a resistance. That the charge has lost a joule, so we say there's 1 ohm of resistance. So I hope that's clear. You can now write down the formal definition. 1 ohm of resistance means 1 volt of electrical energy was converted into another form of energy when a current of 1 amp passes through the resistor. This is the sort of important definition for the exam. What exactly is an ohm of resistance? So you just want even this much would be great.
Every conductor always have the resistance.
Yes.
It's possible to make some conductor without.
Yes. But it is difficult. Very difficult.
But possible.
And it has been done.
Oh.
But it's very difficult and very expensive. But it has been done. Got that? Yeah? Sure. No looking at dirty pictures in class now. What are you doing there? Be good, please. Thank you. Are you showing her funny pictures?
No, I'm telling her SPM results coming up.
What results?
SPM.
What the heck is that?
It's like a big exam in end of high school.
Alright, okay. Do you have friends that are taking these exams? Oh, so these are results of exams you took?
Yeah.
Ah, I see, okay. Good luck. Alright, continue now? Yeah? So, the following picture will help explain the relationship for V, I and R. Because there is a relationship between voltage, current and resistance. This picture here will explain everything. Now let me explain. So, the current, he is unhappy. The resistance, you can see, it makes it difficult for the current to move through. And he has to fight to get in. So, will he have, when he passes through, will he have more or less ability to do work? Less ability. So that's what we mean when we say loses voltage or uses voltage. Having to pass through a high resistance means it has less ability to do work on the other side. Yeah? Of course you don't have to draw this. I'm just trying to really get you to understand this guy, resistance.
Why that guy do that?
Yeah. You all know what internet memes are, don't you? Yeah, okay. Anyways, moving on. So, how do we measure voltage? You can measure voltage using a voltmeter. Not too surprising. And this is what an old-fashioned voltmeter looks like. Now, the ones we have in our experiments don't look like this anymore, but this would be a classic voltmeter. And when you draw a voltmeter, you kind of draw it like this. So, I think it's enough if you can just write down we measure voltage by using a voltmeter. Did anybody see the important video I uploaded last night?
What kind of?
Of the penguin? Okay. Did you see this? No, okay. Oh, you'll see later.
Or is it like a subject?
No, you'll see later. Yeah.
Comedy?
I suppose you could say comedy, yeah. Okay. Next one. As you could probably guess the next one, what would you measure current with? Ampere or resistance. Yeah, you measure current using an ammeter. And here's a picture of it. Get ready. It looks totally different. This is how you measure. This is how you measure current using an ammeter.
What's the important red 3 red 5?
No, don't worry about that. Don't forget about those. Well, this one here, I can't even see it, but I think it's for different levels of current. So if you have milliamps, you can use one. It's for the level of the current. Because you see that you have 3 numbers here. So I think this one may be milliamps and this one's amps. I'm not sure. Okay, did you write that down? We can measure current by using an ammeter. So, how can we measure resistance?
Resistance is by...
or...
Resistance.
Huh? Or we could use an ohm meter. Yeah. Yep. And there's the picture of an ohm meter. Now, you were suggesting using the voltmeter and the ammeter, and that is correct. We don't actually use these machines because they are very inaccurate. It's actually much more accurate to use the voltmeter and the ammeter. They're much more accurate machines than the ohm meter. Ohm meter, we will never use it in this class because it's not accurate, inaccurate.
Why?
But they do exist. You can get them.
Usually we know the lab
Resistance?
Yeah.
Usually, but not for everything. Like if I wanted to know the resistance here, like I don't know what it is, I'd have to do something to measure it.
Well, how do we measure this resistance?
Using this?
No.
Using the voltage and the current? Yeah, there's a special lesson on that. We won't do it just yet, but there is a special circuit that we will study that we can use to measure the resistance. And in fact, it's one of your experiments next semester. Yeah. Okay, continue. Yep. Right, so note, we will not use or study an ohm meter in this class. We will use and study voltmeters and ammeters. Okay, so just to be clear on that. Now, just two things to note. An ammeter, the current must flow through it. So, when you have your ammeter, there it is there, you must have the current flowing through it like this to measure it. Okay, but voltmeters don't work like this. The way a voltmeter works, let's say this is the wire here, and here this is the wire goes in, and the wire goes out. You don't put the current going through the voltmeter. Instead, what you do with the voltmeter is you connect it what's called in parallel. You clip it onto the wire like this. And what the voltmeter can tell you is how much energy was lost between A and B. Now in this picture here, the voltmeter will say 0 volts because there was nothing here to cause a loss in energy. But if I stick in, say, let's say I stick in a heater, then there will be heat energy coming out of this. Where did that energy come from? It came from taking it from the charge. So the voltmeter will see that maybe these guys have 2 volts. They come in, so you know that's 2 joules per coulomb, and maybe it comes out with 1 volt, or let's say half a volt, meaning half a joule per coulomb. Then the voltmeter can tell you how much was lost. So in that example, the voltmeter would read 1.5 volts. Now it's not actually possible to know it here and to know it here. The voltmeter can only tell you the difference. So the voltmeter is not like the ammeter. It can only look at 2 points and tell you the voltage between the points. Or to be more precise, it can tell you the difference in the voltage between the points. Do you understand? And because of that, we sometimes call a voltage a potential difference, a difference in the potential energy. But we'll talk more about this. The important thing is I want you to know that voltmeters, you connect them like this, and ammeters, you connect them like this. Is that okay? I can continue? Yeah? So, a voltmeter requires a voltage between 2 points. In other words, voltmeters and voltages are always between points, whereas ammeters are always at the point. So, here I can say what is the current at A, whereas here I can only say what is the voltage between A and B. Yeah. So voltmeter is always between, and current can be at. Okay, and I drew that already. So, next. The following, of course that's triangle. The following triangle, that's so mistyped. I couldn't, have 3 letters out of place here. Will help explain the relationship between VI and OR. So the relationship is a lot like distance, speed and time. So if I want to know what the voltage is, I can say the voltage is the current multiplied by the resistance. If I want to know the current, I can say the current is the voltage divided by the resistance. And if I want to know the resistance, I can say the resistance is the voltage divided by the current. So this triangle can tell me the missing quantity if I know the other 2. It's a lot like the distance, speed, time triangle. You remember that? This one here is like distance, speed, and time. Yeah? So if you can just draw this triangle, VIR triangle. Got that? Yep. So, let's look at an example. An ammeter measures 250 milliamps flowing through a resistor. The resistor is a light bulb. The voltmeter placed around the light bulb measures 220 volts. What is the resistance? Okay, so what is the formula you use here?
R
R equals
V over I.
V over I. And what's the V?
2,
And the I?
0.25.
0.25. So, calculate please the or.
The voltage measured is 220 volt,
Yeah.
means between 2 points.
Yeah, between
Between
like,
the
if it,
Light bulb,
yeah, if this was the light bulb, then it's around the light bulb. It's 220. Yeah.
this means 220 volt.
Huh?
This between.
Between, yeah. My English is a little bit bad here. I say around, but I think some people prefer to say across. So a voltmeter is placed across the light bulb. But to be honest, I don't really care, because I think everybody understands what you would mean if you said around or across. It doesn't really matter. Okay, did we get an answer? 880. And what's the unit, do you remember? Ohms. Yeah. What symbol is ohms, by the way? What letter is that? Yeah. Capital omega.
It's like the brand of
Is it brand omega? Oh, the watch. Yes, so true. True. I'm too poor to have such a watch, so I very rarely see these things. Yeah. That is true. Okay, continue. Yeah. Right. A 6-volt battery is used to power a toy, not an toy, which has a resistance of 2 ohms. What is the current flowing through the toy? Okay, so the first one, what's the current here? Which formula do we need for that?
I equal V over I.
Yeah, I equals V over R. So V is 6 and R is 2, so what's the current? 3. Okay, so 3 amps, please. You can just write that answer down. Yeah. So V is 6, R is 2, and so I will be 3. Okay. Let's look at part B. I'll open my calculator now. If you leave the toy on for 1 minute, it's on for 1 minute, how many electrons flow from the battery through the toy? So, we want to know how many electrons have moved in this problem. We know the time. So what formula could we use here, or should we use here?
Q equals I.
Q equals IT. Because we know the I, we know the T, so we can get the Q. Now once I have the Q, I'm not finished, because I need to know how many electrons.
Minus 1.
Yeah, well we have this E value, the 1 point whatever, blah blah blah. What do we do with that and the answer we got for Q? Divide them, yeah. So you take the Q and you divide it by this charge of an electron, and then you can know how many electrons. Okay, so calculate that on your calculator, please. Okay, shall we look at the answer? So, here, this is what I got. Is it? Oh, sorry, thank you. 3, shouldn't it be?
Why is it?
Because on the top you got 180 coulombs of charge, and we want to know how many electrons that is. So we have to divide by how big an electron is.
If my calculation don't have that E.
It does not. So you want the value of E? No, it's this E, number 23. That E is a different E.
This is it, right?
Yeah.
So why did it be different?
How different?
What was? Where is it?
Do you have this?
Yeah.
180 divided by this. Ah! You have it upside down. You have it, why is there 2 here? Oh no, that's that
What
one.
row is this E?
I don't know what you're doing, hang on. Yeah. I don't know what's going on.
Why did you divide?
She asked me why I divided. Why did I divide? I want to know how many, if it's 180 coulombs, I want to know how many electrons are in 180 coulombs. So like, I need to divide. What else can I do?
One electron is
1.6 times 10 to the -9
Coulombs. Yeah, of
okay.
charge, yeah.
Right.
Yes. I did say that last time, didn't I? I hope I did. Didn't I?
Okay.
I hope so. Yeah.
Okay.
Continue? Yes? Yeah? Part C. The battery is replaced with a 12-volt battery. How does the current change? Okay. Hint. You may assume R is constant. This is actually not always the case. In fact, it's a law that we'll talk about in the next class. But we assume for the moment R is constant. So let's say the R has to be 2 ohms. What's the formula for R? V over I. So this has to be 2, and the I, what changed? No, the V changed. So this is 12. Now previously we had 2 equals, what was the V previously? 6, and previously the I? 3. So you can see that to keep this 2, what number do I have to put here? It has to be a 6, isn't it? This is the only way I can still have 2 ohms. So if you look, the process of changing the voltage from a 6 to 12, what has that caused in the current to do? The current has increased from 3 to 6. That's what's happened here. Because it's the only way to make a resistance of 2 still. You can think about it like this. I equals V over R. So in the first case, I was 6 over 2, which is 3. And in the second case, I will be 12 over 2, which is also 6. So the answer is clearly the I goes from 3 amps to 6 amps. So you put in a bigger battery, and you also get more current, as well as more voltage, as long as the resistance in the toy is constant. Yeah?
Can you repeat that question?
Yep.
The battery is replaced with a 12 volt.
Yeah.
Battery is, I think it means 6 volts with 12 volts connected.
No, replaced. Replaced means swap.
Means what?
Yeah, yeah. Not extra. Yeah? Did you write that answer down for part C? Yeah. Now, I'll again just tell you this. The R is not really a constant, but in fact, sometimes we can imagine it's a constant because it doesn't change much. But technically speaking, the R in part C is a little bit different to the R in part B. Okay. Continue. By the way, what do you think happens to the R in part C, if you know this? It changes a little bit. It's not really constant. What do you think happens? Yeah, well, it actually, it depends on the toy. Probably increases. But in fact, it could also decrease. This is possible too. Yeah. But again, this will come up later in the chapter. Okay, so no more examples. So I think that gives us time. Yeah, we've got a few minutes to practice some in the workbook. Okay. Yeah. Which topic or what are we talking about? Back here? Yeah, kind of. Go ahead.
What if we increase the time? What will happen for
Well, if we increase the current and the ore stays the same, or nearly the same, then the V should increase too. In other words, it's quite normal and usual for the V and I to increase and decrease together. They move together. Now, it doesn't always happen like this, so that's why I'm saying it's quite usual and normal to see the V and the I increase and decrease together. So if you say, what happens if I increase the current? The V increases. If I decrease the current, the V decreases. When R is roughly constant, yeah. But we'll look at the situations later when the R is not constant.
Why are it changing?
Well, why not? Because I never said that the or, like the V and the I and the or, they can be anything. It's just like distance, speed and time. The distance can be anything, right? It can be here to here or here to there. Yeah. The speed can be anything. Yeah. I can go at any speed. And the time can be anything. And if I know two of them, I can know the third one. But distance, speed and time, like if I said to you, the distance must be constant, you might say, no, because I can change the distance. If I said to you, the speed must be constant, you said, no, I can change the speed. If I said to you, the time must be constant, I said, no, because I can go faster or slower. But with the circuits, we kind of notice that the or is usually constant.
I mean, if this is resistor,
yeah,
it can be everything. It can have every resistor.
Not in real life. In real life, it will have only some values of resistance. I suppose. What am I trying to say? And of course, when I gave the example of the distance, the speed, and the time, it can be anything. But then you realise, well, it can't really be anything because I can't run at any speed. So, yeah, the resistance for that can be anything, but then you realise, well, in real life it's not anything. In fact, it's usually quite a small range of possibilities, and because of this we imagine it's constant. That's what's happening. I can close this slide. Yep.